This is the second module in 6 on databases. In this module, we will be talking about data models. You'll remember from the first module that we said that data can be structured in a variety of ways. The data that you put in a database system has assumptions about how it is structured, and that is a data model. There are different database systems which are built on different types of data model. And in this module, we will review a number of different data models that are used in the field. A data model is a collection of concepts which describes how your data is structured and how it can be represented and accessed. Within a particular data model, a schema is the set of descriptions of a particular collection of data. So I may have my data in a tabular or relational data model, and the schema would then be the description of the tabular format that it's used, the columns, the data value types, that sort of information. The schema is stored in a data dictionary, and that can be represented in a number of different technologies. It can be represented in SQL for relational databases. It can be represented in XML for XML databases, in RDF for triple stores and ontological databases and that sort of thing. And in semantics, which is the knowledge management layer, in the pyramid that we saw in Module 1, that third layer up, a data model is equivalent to an ontology. We'll mention this a bit in Module 6. And an ontology is a formal, explicit specification of a shared conceptualization. It's essentially a schema for a knowledge map. So data models are very important to the functioning of databases. This is an example of a relational data model. This is a data model for a database which is holding genetic and image data about zebrafish. And you can see a set of connected tables, related tables, each with different data types. But there are a number of relationships prescribed between the different tables, and this gives us the data model for this particular database. Any data in this database will be structured according to this data model with the different bits of information that are relevant to a particular data item in the database arranged in this fashion. So the first, and possibly the simplest data model to consider, is the flat or file data model. This is essentially data files that contain records with no structural relationships. It's just the basic data. Obviously, additional information is required to interpret these, such as file format properties. I may have the data in 3 different flat file models on my hard drive. One would be basic ASCII columns, one might be comma-separated variable, one might be in the form of some basic table, HTML table for displaying on a web page. This would be a flat file model. The data is structured in the sense that there are columns and there are rows in this particular case, and then there is some representational information about it. But additional information is required to interpret these files, such as maybe which column is which, and that sort of thing, what the spacing is. The first example, or one of the most famous examples in history about this, is the Hollerith 1889 patent for compiling statistics. This was for census information, and it describes how every US resident can be represented by a string of 80 characters and numbers. The legacy of this Hollerith patent is the screen width of 80 characters that was on many early computer screens and many early computer formats. So it's nice to see that this very first data model already had an impact in the history of computing. Let's say an example of a flat file model is delimiter separated data on my hard drive. Obviously, this is possibly not the most useful data model, and so a more sophisticated one is the hierarchical model. In our hierarchical model, as the name suggests, data is organized in a tree structure. So you have a number of levels. These consist of records of the same type, data records of the same type. This may be that at a particular level there's the same set of field values, same set of measurements of data at a particular level. And then there will also be a field on that level to ensure a particular ordering. In a tree structure, obviously, with levels, you have parent objects and children objects. In a hierarchical model, there is a 1 to n parent-child relationship between two record types. A child can only have one parent, but a parent can have many children. This was a very popular data model in the late 1960s and 1970s. Historically, IBM's information management system, the IMS system, made use of this, and the XML data format that we use today, transport agnostic, platform agnostic data format, is fundamentally a hierarchical model. And so if you're working with an XML document in any fashion, you are actually employing a hierarchical data model. An example of a hierarchical data model is for example, in this case, we have the CAF database of protein structures in the protein data bank. This has 5 levels. It has class, architecture, topology, homologous, superfamily, and sequence family. And you have different types of protein structure in this database at these different levels with relationships between the different levels. As you will see, each level, each item only has one parent, but one parent can have many children. So this is an example of a hierarchical data model in use in scientific data. The network data model, data is organized as sets and records, collections and records. A set has an owner, it has a name, and it has one or more members. A record, a data item, may be an owner in any number of sets and a member in any number of sets. And this allows the modeling of many-to-many relationships. This was a data model formally defined by the codicil specification in 1971 and has been used in a number of applications. An example is shown here of things related to concrete, and you have a number of sets and you have a number of members. For example, you have the joint seal set, which has as members silicon sealant and asphalt sealant, but the joint seal itself is also in the ridgement pavement. The way this differs from the hierarchical data model, though, is that you can see that certain objects can have more than one parent. For example, asphalt sealant is both a member of the joint seal set and also in the patching set. So this is a more networked, less hierarchical. The next data model is object-oriented model. Anyone familiar with object-oriented programming will be very familiar with this. Essentially what an object-oriented data model does is it adds database functionality to object-oriented languages by allowing persistent storage of programming objects. So if I'm using an object-oriented language like Java, I have a complex object that I'm using in Java, and I want to make that persistent. I want to store it so that I can retrieve it offhand later. An object-oriented database may be the sort of thing that I want. One of the advantages of actually having a specific object-oriented database, which allows the storage of objects, is that it means I do not need to convert information from a database application representation all the time. The object-oriented model allows me to already make use of object-oriented structures for doing this. This means that less code is required, and also that because I may already have a database structure which maps to the types of objects that I'm using in my programs, there's a more natural modeling between the two. This can be very good for very complex data objects, and when you have very complex relationships between different types of data objects. And there are a number of commercial databases out there, a number of free databases as well, which make use of this particular data model. Here's an example where I'm dealing with maintenance reports, and I have an object-oriented model where I have an object which is a maintenance report, and I have a second object which is maintenance activity, and there is a relationship between those two, and then what I'm storing are instances of those objects containing the relevant information about those particular data structures, according to those data structures. Possibly the most famous or the most widely used data model is the relational data model, and we will be talking more about that and the technology supporting that in the next 3 modules. In the relational data model, data is organized as relations, as attributes, and as domains. Those are the formal names. More prosaically, a relation is a table. Relational model databases, relational databases, essentially work with tabular data. So a relation is a table which has attributes, which are the columns, and it has rows, which are the tuples. And the domain in a relational model is the set of values that the attributes that are allowed to take. That is the set of values that the columns of the table are allowed to take, are allowed to hold. And within the relation, within a table, each row is unique. Column order is immaterial. Doesn't matter what order you have your columns. And each row contains a single value for each of its attributes. So that means that each row, there's only a single value for each column. There are some relaxations of these particular constraints in variants on the relational database model, but as it stands, this was originally proposed by Codd in 1969-1970 and has formed the basis for all the relational database technology that drives our lives today, underpins our lives today. This is an example of a relational model. In this particular case, we have 3 relations, 3 tables. They each have 2 attributes, or one of them has 2 attributes, 2 columns, the other 2 have got 3 columns, 3 attributes, individual rows, and then you can see there are relations between them where the particular column, particular attribute in one of the tables is expanded in one of the other tables, activity code with information associated with it. The associative data model. In this particular way, data is modeled as entities having a discrete independent existence and associations. So you could envisage this as a set of facts and then the connections between the associations between those facts which are meaningful. It's organized as items, an identifier, a name and a type, and in the terms of links, links also each have an identifier, they have a source, they have a verb which tells you something about the nature of the link, and they have a target. Example of how I may represent a particular data item in such a model is, say I was running a database of flight time arrivals and departures. Flight BA1234 arrived at LAX on the 10th of April 2012 at 1:25 p.m. The items that I would have, the individual facts, each of these would have an identifier, a name and a type. They would be the flight, BA1234, the location, LAX, the date, the arrival time, and then arrived at, on, and at. And then I would have links putting those together. So I'd have flight BA 1234 arrived at LAX, and then there would be on 10th of April 12 and at 1:25 p.m. So I'd put that together in that way, and they could store that in an associative way. This is quite similar to the way a lot of the web works, and you can consider the web to be an associative data model in some contexts. Other data models that we aren't going to talk about really, but you may be interested in, is semi-structured models. These are graph-based for information that cannot be constrained by schema. The web, for example, in its more general way, is a disparate collection of facts, but we could consider it to be semi-structured, and we could try and impose some sort of interface layer on top of it to make management of retrieving that information more viable. And then we have object relational data models, which are trying to combine some of the features of the object-oriented model with relational database models. And in that, for example, we add object capabilities to relational systems. An example of this is adding location tasks to relational databases for doing spatiotemporal work, geographical work, storing geographical data. And with that, we will finish this module. Thank you.